Welcome again. We're going to do a little bit of a lightboard demonstration here. I'm hoping I accidentally left some of my markers open, so they may be dry. But let's talk about errors. We're going to talk about errors. And what we're going to do is we're going to look at some of the errors that we can have in our system. Let's talk about, first of all, this is a sample exam. So let's talk about the sample exam issue that we've had. I gave that out to you. We've worked it all out, so now we all know how we're going to do that. I'm going to redo this. It's going to be 1 over s plus 10, and there's going to be some kind of a thing here. This is going to be plus. I'm going to always kind of in the background leave this disturbance force on there. And then we're going to do this is 1 over s plus 1. I'm not sure I put these in the right order. I did put them in the right order, but maybe I shouldn't have put them in that order. That's okay. So here's x. And then what we're going to do, this is going to be input. We don't know what the input is. So this is the open loop system. And what we're going to, what we've done all the time, what I've been saying to do is let's do this. Hey, let's go ahead and use our magic control law, where the magic control law says Kp times xd minus x. Okay, so this one's running out of juice, so I'm going to put it over somewhere else. I left some of them open. I'm going to rewrite this. Kp times xd minus x. Okay, sorry if that's a little bit funky. Maybe it still is. There's a couple of these that were still. So let's go ahead and do that in block diagram form. We're going to go and do that. I'm afraid that one's going to be bad too. Let's see. This is going to be Kp. And this is blue. It's not even any good. We may only have one color today. Where this is going to be x desired plus minus x. And we're going to put our feedback loop going around this way. And this is a special kind of feedback loop. It's called a unity feedback loop. It's a unity feedback loop because there's a 1 in there. And so what we'll do, the errors, the way they talk about errors in the chapter, there's all kind of like a bunch of formulas that you can use. But what we know is that for our system, what we can do is we can look at the transfer function. The transfer function, T of s, which is equal to the output over the input. I'm going to teach you a different way of remembering the transfer function formula. I want you to remember this one. That's the feed forward over 1 plus the feed forward times the feedback. So I want you to remember that one. And then at the same time up here, I'm going to say, hey, we're going to put this into a different form, and it could look like this, where this is G of S. And this is the unity feedback. I should put a little space here. We should leave a little space for a Kp plus minus. Okay, so we've got that. But I want to point out to you what G of S is. Actually, in the most general case, we should actually also include an H of S. And so I want to tell you a new one, that G of S is equal to the numerator of G as a function of S, and then the denominator of G as a function of S. And H of S is similarly the numerator of H over the denominator of H. Is it okay if I don't put S's there? Because I don't want to. And now I'm going to put this feed forward over feed back in terms of these parameters. And then it's going to be the numerator of G over the denominator of G. It's the feed forward divided by 1 plus the feed forward numerator of G, denominator of G, times the feedback, which is the numerator of H, times the denominator of H. We've talked about this every time. You have to clear these fractions. This is dg. Uh-oh. Oh no, it's hard to erase this stuff properly. dgdh over dgdh. Right? We're going to clear that fraction. And so what we're going to see is that the transfer function for this, the overall closed loop transfer function, sometimes I'll put closed loop so we remember what the transfer function is. The overall closed loop transfer function then is going to be the numerator of g times the denominator of h divided by the denominator of g times the denominator of h plus the numerator of g times the numerator of h. Okay, so there we've got those things. Now, a lot of times, sometimes, you'll see I kind of didn't put this kp in here, and sometimes people just like absorb this kp into the g part. And so, a lot of times they just might like say, oh yeah, well, you know, like that's got a little bit of a kp on it here, and this has got a little bit of a kp on it here, and so in the end, this has got a kp here, and this has got a kp here. So sometimes they'll just add some of that stuff on there. And so what we can look at is we can look at what the steady state gain is for this. Right? So let's look at what the steady state gain is. So there's a couple of different ways that we want to try and take a look at this. Let's look at what the transfer function for this system is. T of s is equal to, so it's the numerator of g times the denominator of h, that's just 1, divided by the denominator of g, s plus 10, times the denominator of h, s plus 1, s plus 10, denominator of g times the denominator of h, which is just 1, plus the numerator of g times the numerator of h, which is kp, and this works out the same. So fortunately, we already know what the answer is because we've done this homework assignment. This is s squared plus 11s plus 1 plus 10 plus kp. Right? So that's what the whole feed was. And if we wanted to, we might want to put a little parentheses around here because this is s to the 2, s to the 1, s to the 0. All right. And so if I want to look at what t of s equals 0 is, then that's easy. That's just kp over 10 plus kp. Right, so, and we can figure out. Now, if I want to know what the error is, it turns out what the error is going to be, it's going to be, this is the transfer function, which is x over xd. Then if I'm looking at the error, sometimes what we'll do is we'll just put a little line here. We'll just say, oh, you know, I want to know what the error is. And what I'll do is I'll just subtract. I'll subtract this and add this. This is what I want it to be. And then I'll subtract what it actually is. And then that'll give me the error, which is going to be 1 minus t of s equals 0. So there's a number of different formulas that they go through in there. So I'm going to kind of go into some of the formulas, but I want to make sure that we all understand this part of it first. Some block diagrams, some natural block diagram stuff, the block diagram reduction, the overall transfer function for our system, and then also what the steady state gain for the system is and how the steady state gain differs from the steady state error. Right? The steady state error is 1 minus that. Well, now we have to try and generalize everything. And oftentimes what happens is when we try to generalize things, you know, one of the issues that happens is that these guys always like say, oh yeah, here's a problem. And it's always a much harder problem than whatever you figured you were ever going to be doing before. And so here I'm going to do problem 23 in the textbook. And basically problem 23, so in the same vein as our unity feedback system, they're going to go over here, they're going to say, oh, you know what? All unity feedback systems look like this. G of S. It's kind of implied that there's a KP involved. And then also, it is a unity feedback system. There's always a minus there and a plus there, so there's some nuances with that. Okay, so that's unity feedback system. And in problem 23, what they're telling us is that G of S is equal to, so they always kind of put this KP. This is bad. I use the KP. They use the KP for something else. So when I get to their KP, I'm going to rename their KP to something else. This is S squared plus 6S plus 6 divided by S plus 5 squared times S plus 3. So again, this is, everybody has their own kind of little things that they do. And, one thing that we might want to even do is just try and get this into a ratio of polynomials, even if we can do that. And I'm just going to tell you how to do that. We can do the convolve, C-O-N-V, I should use lowercase, because in MATLAB they have a thing for this. Like, I don't know, convolve means to put them together the right way. Here is, we're going to convolve this 1 S squared plus 5 with S squared plus 5. And then that'll give us the right answer, which if the answer here is S squared plus 10S plus 25. So that's what that MATLAB command will give you. And then I'm going to try this, even though I found some other colors, and we'll see if the other colors make any difference or not. But one of the things that we can do, so this is, I just convolved these two, and I'd like to convolve all three of them now, so I'll just use MATLAB. I'll just convolve that with this, comma, S plus 3. And parentheses, boom. And now I'm all done. That gives me, what MATLAB is going to give me is this answer. 55, and 75. So that's like S cubed plus 13S squared plus 55S plus 75, right? And so without too much more trouble, like, I'm not 100% how these ones look, so I'm going to try a couple of different ones of them, and then you'll be my guinea pigs on my Lightboard thing. So what we can do now that we know what the numerator is and what the denominator is for our unity feedback system, and we know the formula, the kind of modified formula for feed forward over 1 plus the feed forward times the feedback. We have a modified formula for that. And now what we can do is we can look at the closed loop transfer function, which is equal to the output over the input, and we're going to be able to say, oh, okay, so that's the numerator of G, S squared plus 6S plus 6, times it's the numerator of G times the denominator of H. That's just 1 because we're a unity feedback system. And now we're going to look at the denominator of G, which is going to be S cubed plus 13S squared plus 55S plus 75. Oh my goodness. I don't think I did this all quite right, but. So it's the denominator of G times the denominator of H. Oh yeah, I did. Phew. Okay, because that's just 1. Oh, we need to make this line go much farther out. Plus the numerator, so this is the, right, so it's denominator of G, no, numerator of G times the denominator of H, denominator of H, divided by denominator of G, denominator of H, plus the numerator of G times the numerator of H. So if you care about formulas, there's a formula for it. So here is the denominator of G times the denominator of H, Okay, so now I'm going to do the denominator times, this is just the numerator of G times the numerator of H. The numerator of H is just 1, so this is really just the numerator of G. So this is going to be KP S squared plus KP times 6S plus 6 KP times 75, right? And so if we wanted to know what the whole denominator is here, maybe I'll put this in dashed lines or something. I don't know. I better write. I'll see if I can get. I'm going to test out some different colors here. Let's try green. See if green works very well. So this is going to be s cubed plus 13 plus kp s squared plus 55 plus 6 kp s plus 75 plus 6 times 75 kp. So that's the denominator. And so what we know is, we know from our earlier discussions that as long as the roots are on the left half plane, then we're good. We've got stability. But if we wanted to, we could also see what would happen if we wanted to look at t of s equals 0. If we want to look at t of s equals 0, that's just going to be kp times 6 over I think I made a mistake here, right? Did I make a mistake here? Why don't I just leave big blurry mess there? Because that's the numerator of that. And so then this shouldn't be there either. I'm just saying. You know, a little math, you make some mistakes when you're doing math. So what's in the numerator is 6 kp, and what's in the denominator is 6 kp plus 75. Right? So that's what s equals 0 is equal to. Again, what we know is that as long as you do this the right way, here, we'll do it this way. So when t of s equals 0, sorry, I ran out of space, kp times 6 divided by 6 kp plus 75. So if we make kp big enough, we can get it equal to 1. Why do we want it to be equal to 1? Remember why we want to get it to equal to 1 is because the output over the input is equal to t of s. And if we do this as t of s equals 0, that is the steady state. And if that happens to be equal to 1, then what that means is if the output over the input is equal to 1, that's s equals 0. I don't want to forget, these parts are important, but they're easy just to gloss over. That means that the output is equal to the input. Yay! And that's what we want. See? So we're all good to go with that, right? All right, so what we've done is we've taken problem 23. We've kind of gone in here. You know, they have a more specific set of formulas. I may be dealing with that a little bit here in a minute also. But basically what I want to show you is that, again, you know, what we're shooting for is to see what the steady state gain for our system is. We get to choose this gain kp, and I'm hoping that in the homework assignment that I gave you that you're going to see, oh, by the way, you know, there's some trade-offs. I can make kp higher, I get more oscillations and stuff like that, but it makes, you know, it makes the steady state gain better. Maybe you're going to see some of that. Oh, goodness gracious. Formulas. Formulas. Everybody likes formulas. All right, let's get some formulas together. I'm going to have to remember how to do all these formulas. So you're going to help me. But let's not use like problem 23. Let's go back to something that we're going to use over and over again. You're going to use for the rest of your life, which is, let's look again at the motor equations. M-O-T-O-R equations. Okay, we've gone through and worked these out from first principles. That works all the time. Those are good. And now let's see what we're going to do with the motor equation. So we've got Km over Rm. We've got N. That is the gear ratio. Plus, now I always like to put this D in here. We can go back and later we can go back and redo all these formulas with D as the input. We've learned how to do that too, right? And then we're going to do 1 over J equivalent S plus B equivalent. So this, if you look at what this does the relationship between this and omega equals theta dot. Right? So that's the speed of the motor, and if we want to know what the position of the motor is, then we have to do our integration. We have to integrate once and we get theta of the motor. I'm using theta now, and this is Dn, right? So this is the input, Dn. And of course, in the perfect world, this whole business here, okay, I'm going to try using these other colors again. I'm not sure if they're any good or not, but this whole business here, this is G of S in the chapter 6 lingo. Yeah, okay. So G of S, in this particular case, is going to be, can I put numbers into it? Can I just add numbers to it? Because I forgot I was going to do numbers. All right, so I'm just going to put numbers in this one. And that's going to be 0. I'm just going to do 0.413. This is going to be 1 over 7.85, 7.58 e minus 5 s plus 0.0044. And then here's the 1 over s. So if I just put numbers into it, that's all fine. Here's what, if you put the input in, if you put a voltage to this, if you put a voltage to the motor, then the angle omega gets to be a constant. That's a first order thing. Omega equals theta dot, and then theta also then just keeps going and going and going. And if what we're trying to do is control the motor. Now there's another way to do this, and I'm going to just do it. So suppose I divide through, suppose I take a factor of 7.58 e minus 5, I think those are the right numbers, 7.585 e minus 5. Suppose I take that out, then what I'm going to get is I'm going to get an open loop transfer function. I'm going to get a G of S that is equal to 545 divided by S squared plus 58S. So see, even though we know the background here that, oh, what is J equivalent is equal to J of the motor times N squared plus whatever the output, like we know all those things, but in the end, we can just put some numbers in there, and now, if we're control systems engineers, we're going to start here because we don't care where these numbers come from. We don't even care where these numbers come from, okay? So what I'm going to be able to do here is I'm also going to be able to say that the proportional time constant, so I'm calling it Kp here, Kp is equal to the limit as s approaches 0. It's the limit as s approaches 0 of G of S. And we can do that one. Oh, the limit as s approaches 0. That's 0. Oh, wait a minute. The limit as s approaches 0 of G of S is not 0. Remember, it's infinity. So that means that E of S, the steady state of S equals 0, the steady state error for this system, this is called a type 1 system because it has one free integrator in it, right here. And so the limit as s approaches 0 is going to be 1 over 1 plus Kp. 0. So that means the error is 0. For this system, the error is 0. Right? Now, for this particular motor system that we have, that means that what we're doing, again, here's what we're doing. We're saying x desired plus minus, we're putting the proportional gain in there, Kp, that's not this Kp, and we're doing 545 over s plus 58. I'm kind of breaking this up in a number of different ways for you. 1 over s, right? And then here is x. And what we're saying is, oh, this is the unity feedback system that we're talking about here. That's the unity feedback system that we're talking about here. We're going to, and so let's design the controller for this. We know how to do this design controller for this. We've done it before. So what we're going to do is we're going to say, so what we've got is that the overall transfer function, T of s, is equal to the output over the input. This is equal to x over x desired. This is going to be the numerator of g times the denominator of h, which is just 1, divided by the denominator of g, s plus 58, s squared, that's the denominator of g, times the denominator of h, which is just 1, plus the numerator of g, kp, times 525. Numerator of g times the numerator of h. Right? And so what we also know is that right here, like 2 zeta omega, I'm sorry, I'm trying, oh no, I'll never get rid of that. Okay, I get it. 2 zeta omega n is equal to 58, and omega n squared is equal to kp times 545. And so we can just choose a zeta. I'm going to send out a thing that says like, oh, why should you use zeta 0.707 in the absence of any other, criteria? Use zeta equals 0.707. So we'll choose a zeta that we think is acceptable. Maybe a lower zeta, maybe zeta of 0.5 is acceptable. We'll try that. And then what we can do is figure out what kp is. Let's go back to our kind of like, if anybody doesn't mind, I'm going to change my sample exam question ever so slightly. 1 over s plus 10, 1 over s plus 1. I like it better this way. Maybe I'll show you this later, but so clearly it doesn't really make that much difference. We're going to put our disturbance force in here, plus, where this is the input, this is the output. Maybe I call this x. Maybe this is the input variable. So, formulas are always good. One of the things that happens with this stuff is that when you put, when it comes time, when the time comes, I'm going to try some of these old ones here. When the time comes to put your proportional gain in here, Kp, a lot of times, even though we haven't really said this yet, there's a lot of books that include this Kp, like they already know this is going to happen. And they just include that in. Because what they'll do, a lot of times what they'll do next, the next step, is that they just say, oh, well, I'm going to tell you what g of s is. I'm going to tell you that g of s is going to be Kp over s plus 10, s plus 1. All right, so one of the things that you'll see now, x, and this is the input. One of the things that you see out of this for sure is that it didn't make any difference which way I put this. I put this in. Usually the faster dynamics are up here. That's because these are associated with amplifier dynamics and stuff like this. And the slower dynamics are here because those are associated with the physical parts of the system. All right? And so now we have our system here. And what we might want to do, what we know, the way this stuff always is going to work now is that this is the error. We can call that the error plus, minus, and we'll put our feedback gain on there. We're good to go with that. And what we're going to do is we will find out that the error is equal to oh gosh, the book does it this, they call it R, that's the reference signal, and they call that C, the output signal. But that's okay, let me still do what R is. R is equal to, no, E is equal to R minus E G. So we do our, I'll do my algebra. E plus EG equals R. I'm going to do a little bit of that. This is E times 1 plus G equals R. Remember what G includes is the KP here. And then what I'm going to do is I'm going to say, oh, if I want to know what the E is, as a function of the E is equal to R over 1 plus G. And then, if I want to know what E, so they use the E of S equals 0, the steady state error is the limit as S approaches 0 of S times the function, which is R over 1 plus G. See how that works? And sometimes we might even call this is going to be, so this is kind of like, I'm trying to make sure I do this right. It's not quite, I might not quite do it right. Remember, this is G of S, and if I put in S equals 0 everywhere, well, let's plug it in. I don't know. Let's plug it in. Oh, sorry, because I know what R is. Sorry, okay, I was just missing a point. What is R? R, well, let's do it this way. R of T equals U of T. That means if when I do the Laplace transform of both sides, it means that R of S equals 1 over S. And that way, when I plug this in, it's the limit as S approaches 0 of S times 1 over S divided by 1 plus G of S equals 0. Right? So we've got all that stuff down. Oh, good. Thank goodness, thank goodness. I'm just going to go ahead and get a different color. Okay. Those cancel. And in this particular case, G of S equals 0, G of S equals 0 is equal to, well, there's a KP in there. So it has to do with KP. But for now, we're just going to let KP equals 1. It's going to be 1 over 10. G of S equals 0 is 1 over 10. That means that KP, in the book, they use K, but I'm changing it a little bit. KP is equal to G of S equals 0, which is 1/10. And that means that our overall error, E of S equals 0, the steady state error for this particular system is going to be 1 over 1 plus KP, which is going to be 1 over 1 plus 1/10, which is going to be 10 over 11. They're just going to use this KP as an error constant here. Voila, a clean slate, tabula rasa, as it were. All right, so what happens now when the R is a different kind of input? We can say that E of S is equal to R over 1 plus G, G, 1 plus G, but sometimes R is something else. And they give you several different kinds. So we know that U of T gives me R equals 1 over S. I can use the ramp function, that gives me that r is equal to 1 over s squared. And then also, I'm going to give you a parabolic, parabola. This is acceleration. So this is position, velocity, acceleration. That means that r is equal to 1 over s cubed. You go look at those out. Those are like, oh, you have to go to the table of Laplace transforms. And so, what we know is that E of s equals 0, the steady state gain is equal to the limit as s approaches 0 of r s r over 1 plus g. So that's a formula. Everybody loves formulas. Here's a formula for you, baby. And if we plug all this stuff in, then we're going to get this way. This is the limit as s approaches 0 of s 1 over s squared, because that's what r is really, right? And so this is 1 plus g. We're going to just keep doing this math of the limit as s approaches 0. You know, I already did my limit joke, so you know that one. Okay, so one of these s's cancel out. This is going to be 1 over s plus sg, right? And so we know that when s equals 0, this is going to be 1 over 0 plus 0g, which is going to be 1 over 0, which is going to be, the steady state error is infinity. So what I hope you're not doing is, if you're on your battleship here, this is a battleship, and here's an airplane flying in to get you. Here's my airplane. Here's my airplane flying in to get you. And my airplane is going at a constant velocity, v. That the constant velocity is the s squared part. And here you are, you've got your cannon hooked all up to shoot that airplane down. And what you're going to do is you're going to say, like, well, I know where it is because my radar tells me that's desired. And so all I'm just going to do is I'm just going to point at it. I'm going to put my control system around it here, and I'm thinking, wait a minute here, because as this thing flies by, your error just keeps getting bigger and bigger and bigger, and they bomb you and you're dead. Sorry. Okay, so formulas. Formulas are always good.